Green energy. Everyone is talking about it, calling it the energy of the future. Everyone says it's the solution to global warming. Everyone wants it, so what's holding it back? Why is it barely used? Well, one big reason is that the two most common forms of green energy, solar and wind, are highly intermittent and unpredictable. The sun doesn't shine on cloudy days and most certainly does not shine at night. The wind can blow day and night, but in varying degrees of intensity and sometimes not at all. We have the answers to these questions and the solution to this problem. Our system is designed to store sufficient amounts of green energy to supply grid-scale amounts of electricity equivalent to that produced by a coal-fired power plant. Our patented system manufactures, stores, and transports grid-scale amounts of green energy produced by solar and wind farms. It does this by using electrolysis to produce hydrogen and oxygen gases. It then stores these gases in underground chambers constructed in such a way that the surrounding rock strata can be used as reinforcement. Energy requirements for mechanical compression of the gases are eliminated by using hydrostatic pressure to compress the gases for storage and transportation. No new technologies or major breakthroughs are needed for this system to start being implemented. This presentation will answer questions that we are commonly asked concerning our newly patented method of storing green energy. We will discuss how the system works and what we have done to demonstrate it, and compare the cost to a coal-fired power plant method of generating electric power. We will use a series of diagrams to explain how the system works. We begin by showing a cross-section of landscape depicting a section of a lake on the surface and ground below the surface. In this discussion, we will use various icons to represent key features of the system. The icons in the upper right corner represent a solar and wind farm, supplying electricity to the commercial electrical grid. This is the current state of the art of solar and wind power generation. The system is functional and provides green energy as long as the sun is shining and the wind is blowing. When the sun isn't shining or the wind isn't blowing, electrical energy must come from conventional sources, namely fossil fuels such as coal or natural gas. In this drawing, we show excess electrical power from the solar and wind farm being sent to a hydrogen generator that will most likely be some type of electrolyzer or fuel cell. We now add an underground chamber. These chambers would typically be 6 to 20 feet in diameter and 1,000 to 2,000 feet deep. The surrounding rock reinforces the chamber's wall so that high pressures can be contained within the chamber. These chambers would be drilled into the earth using the same technology as is used to construct mine shafts in underground mines. Here we show the chamber being connected to the lake by a pipeline that extends to the bottom of the chamber. From this pipeline, the chamber is flooded with water. In this illustration, the red line depicts hydrogen being pumped from the hydrogen generator into the top of the underground chamber. As the gas accumulates in the top of the chamber and increases in volume, some of the water is forced out of the bottom of the chamber and back into the lake through the same pipe that was used to fill the chamber. The gas pressure must overcome the weight of the water in the chamber to be forced out of the chamber. This is what is referred to as hydrostatic pressure. At any given time, the gas pressure in the chamber is determined by the difference in the water level elevation in the chamber and the water level elevation in the lake. In this example, at a water level depth of 600 feet, the gas pressure is 258 psi. As more and more gas is forced into the chamber, more and more water is forced out of the chamber. Hydrostatic pressure increases at a rate of 43 psi per 100 foot of depth. As shown in this illustration, at 1600 feet, the gas pressure would equal 688 psi. When the 2,000 foot deep chamber above is completely filled with gas, the gas pressure would be 867 psi. When the sun is not shining and the wind is not blowing, or maybe even during a peak load, the stored hydrogen can be transported to an electric power plant where it is converted back into electricity either by burning the gas or by use of fuel cells. As the gas continues to be removed from the chamber, water flows back into the chamber. The water flowing back into the chamber acts as a piston pushing out the gas under the hydrostatic pressure created by the inrush of the water. This process acts in reverse to the filling of the chamber with gas. As more gas is removed and water rises in the chamber, the gas pressure decreases accordingly. But at all times, the gas remains pressurized to some degree. As shown here, when the water level reaches the 1,000-foot depth, the hydrostatic pressure and gas pressure would equal 430 psi. Once all the gas has been removed from the chamber is once again completely flooded, and the cycle can be repeated over and over. When the hydrogen is converted back into electricity, the process efficiency can be greatly increased by using pure oxygen rather than pulling oxygen from the atmosphere. When the water is broken down into hydrogen gas by electrolysis, oxygen gas is also produced. It is a simple matter to construct additional underground storage chambers to also store the oxygen gas, shown by the orange gas in the chamber on the far right in this diagram. Also shown are two hydrogen storage chambers. The reason for this is because when water is broken down by electrolysis, there are 2 molecules of hydrogen produced for every atom of oxygen. Now that we've shown that both the hydrogen and oxygen gases can be stored, if more storage is desired, it is simply a matter of constructing additional storage chambers. We have now shown that it is possible to store large amounts of pressurized hydrogen and oxygen gases produced by electrolysis and using hydrostatic water pressure to keep it pressurized in the chamber. In this drawing, we are moving the electrolysis process from the surface to the bottom of an underground production chamber, very similar to one of the storage chambers. By doing this, both hydrogen and oxygen is generated under pressure, eliminating the need for mechanical compression and improving the efficiency of the gas production. As shown in the enlarged area on the bottom right, the hydrogen and oxygen is captured in tubes to keep them separate. As was illustrated previously, the gas is transported and stored in other underground chambers. Now that we have explained how, in theory, the concept works, next we will provide a small working model to demonstrate that the system does indeed work. The working model will represent this configuration, whereby we have an underground production chamber on the left with electrolysis producing hydrogen and oxygen gases that are stored separately in 2 hydrogen chambers and 1 oxygen chamber. On the left side of the screen is a diagram of our working model, and on the right side is the model itself. Shown is a solar panel, which represents a solar farm, which provides power for the electrolysis. Also shown are 4 tubes, which simulate the chambers. The production chamber is on the far left, followed by 2 hydrogen storage chambers and 1 oxygen storage chamber on the far right. In this animation, we are showing the hydrogen and oxygen being produced in the production chamber and being transferred to the storage chambers. First, we see the hydrogen being transferred to the hydrogen chambers, forcing the water out of those chambers. In a similar fashion, we see the oxygen being generated, transferred to the oxygen chamber on the far right, also displacing the water out of that chamber back into the surface reservoir. Now that we have the hydrogen and oxygen gases captured, we can use them on demand to generate power. First, we see the hydrogen being released from the 2 hydrogen chambers and the water being restored to the chambers as the hydrogen escapes. In the same way, we see as the oxygen is being released from the oxygen chamber, the water re-enters that chamber and refills it. Now that we've shown the simulation, we will show the same functions in our working model. Here we see the sun shining onto a solar panel, which we'll use to provide power to the electrolysis in our working model. The electrolysis occurs at the bottom of the production chamber. Here's a close-up of the electrolysis portion showing the two electrodes which produce the hydrogen and oxygen gases. We see the gases rising in the tubes. The tube on the right is the hydrogen, the tube on the left is the oxygen. We can see there's a lot more hydrogen than oxygen being produced. Here we are showing the hydrogen gas being transported over to the two hydrogen storage chambers. In a similar manner, we show the oxygen being transported over to the oxygen storage chamber on the far right of our working model. Next, we show how the hydrostatic pressure pressurizes the gas. Here we see the two hydrogen chambers, the gas entering into the top of the chambers, forcing the water out of the chambers. You can see on the left-hand portion of the slide that the gas pressure is increasing as the gas volume is also increasing in volume, causing the water and the hydrostatic pressure to activate. Once the gas is captured and released from the chambers to generate power, we can see that the water refills the chamber, and you can see that the gas pressure in the chamber declines proportionally. Next, we will show the power generation portion of the operation. We will be using a fuel cell to take the hydrogen and oxygen gases from the storage chambers and converting them into electricity. As I open the valves to release the hydrogen and oxygen gases from the storage chambers, feeding the gases into the fuel cell, you can see that the voltage on the voltmeter is increasing. This completes the process of taking sunlight, converting it into hydrogen and oxygen, and then transforming it back into electricity. Next, we'll show how the underground storage chambers are constructed. The underground storage and production chambers can be constructed using a method called blind bore shaft drilling, a type of drilling that is commonly used in the mining industry to construct ventilation shafts. The drill bits used in this method of shaft drilling can be quite large and often weigh several tons. They are usually transported to the work site in sections and assembled on site. These types of drill bits and the equipment needed to drill with them already exist and are used worldwide on a daily basis. The holes drilled using this method commonly range in size from 6 to 20 feet in diameter and can be drilled through any kind of underground strata. This photo shows the drill head inside the hole and the drilling process taking place. During the drilling process, sections of precast liner are delivered to the drill site as shown here. This manner of shaft construction allows for all work, including the drilling and the lining of the shaft, to be safely done from the surface, with no underground access needed. This is the view you would have standing on the surface and looking down into the chamber. These chambers can be drilled and lined to depths in excess of 2,000 feet. Shown is a completed underground mine ventilation shaft. The major difference between constructing mine shafts and underground storage chambers is that the chambers will be capped and sealed so that they can contain highly pressurized hydrogen and oxygen gas. This capping process is also routinely done in the mining industry whenever a mine is closed and its ventilation shafts are no longer needed. These production and storage chambers can be safely and efficiently constructed at any location with existing technology and equipment. We would like to thank Abigildy, a world-leading blind boring contractor, whose photos were used in the making of this video. Now that we have shown that these chambers can be constructed using conventional technology, can we show that they are cost effective? You might be surprised to learn that the cost to build a 500 megawatt power plant is $1.5 billion. Many of the existing fossil fuel power plants can be retrofitted to convert from fossil fuels to hydrogen, thereby minimizing the infrastructure cost. The coal cost for a 500 megawatt power generating plant is about $50 million a year. That is the cost we are competing against. The cost to construct an underground storage chamber is about $5 million. 6 20-foot diameter chambers that are 2,000 feet deep would supply a 500 megawatt power facility for a 24-hour period. Therefore, for $30 million of storage infrastructure, which would be a one-time cost, the effective fuel cost can be reduced to zero, assuming the solar and wind power supply is available to generate hydrogen from electrolysis. And then there are several consequences of climate change: floods, droughts, hurricanes, that have tremendous costs associated with them. When these are considered, the cost of moving to a hydrogen-based fuel economy is negligible. And when you consider the cost of nuclear waste reclamation and the impact of an earthquake or a terrorist act that could damage a nuclear plant, nuclear is not a viable option. Green energy is the solution. This completes the discussion of our patented system of storing green energy. We have the idea. What we don't have is the resources to develop it. For more information about further technical details, as well as application of our patented green energy storage system, check back soon for additional videos.